Hi, this is your video for Chapter 4 about linear regression. So we're starting with a little review of Section 4.1. And in this section, back at the beginning of the semester, we talked about the linear correlation coefficient R. It's a numerical measure of the strength of the relationship between two variables representing quantitative data. So when we're doing this, we're going to have paired sample data. Sometimes we call this bivariate data. And we find the value of R, usually using technology, and then we use that value to determine whether there's a linear correlation between the two variables. In this section, we're only considering linear relationships, which means that when we graph, the points approximate a straight line pattern. So here's some definitions. A correlation exists between two variables when the values of one are somehow associated with the values of the other in some way. The linear correlation coefficient, R, measures the strength of the linear relationship between the paired quantitative x and y values in a sample. Now here's some scatter plots that show what different R values look like. So for this one over here, if we look at all these data points, there seems to be a linear pattern. So we would say that this one has a positive correlation because the linear pattern is going up as it goes from left to right. And this is a fairly strong linear pattern, so the R value is 0.851. In this one on the right, our linear pattern is going down from left to right, so we would say this one has a negative correlation. This one is even closer to a straight line pattern, so our R value for this one is negative because it's a negative correlation, and it's 0.965. That's very close to -1. Here are a couple more scatter plots. This one you can see the data points are just all spread out, so we'd say there's no correlation, there's no pattern that we can see, and our R value would be 0 or very close to 0. And this one, there is a pattern, obviously, but it's not a straight line pattern. So this is a relationship, but it's not a linear one. So in this one also, our R value would be very close to 0. Here's some properties of our linear correlation coefficient. First of all, the R value that we're talking about is always going to be somewhere between -1 and +1. If we convert all the values of either variable to a different scale, that doesn't change the value of R. Also, the value of R is not affected by which variable we choose to be x and which we choose to be y. We can switch these around and it still won't change the R value. The R measures the strength of a linear relationship, and the R is also very sensitive to outliers. They can dramatically affect the value. Let's look at an example. Because colas tend to replace healthier beverages and colas contain caffeine and phosphoric acid, researchers wanted to know whether cola consumption is associated with lower bone mineral density in women. The table lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. Create a scatter plot of the data and find the correlation coefficient. So here's our data. Now we can use StatCrunch to create our scatter plot, and to do that we would put these two columns into the data editor in StatCrunch. So the number of colas per week would go into one column, bone mineral density would go into another column, and then we would do, in StatCrunch we would do graph and scatter plot. And that would give us a scatter plot like this. So this is just treating each one of those pairs of numbers as a point. So for instance, this one would be for 2 colas per week and a bone mineral density of somewhere between 0.87 and 0.875. And we can also use StatCrunch to find R. And that's really the easy way to do it because the formula for R is pretty complicated. So to do that, if we have our data in StatCrunch already in our two columns, to do the linear correlation coefficient, we would do stat and then regression and then simple linear. And once we did that, this is what the kind of thing we would come up with. Right here is where it will tell us what our R value is. So the R value for this one is negative 0.806 approximately. Since we've already talked about hypothesis tests, we're also going to look at conducting hypothesis tests to determine whether there's a linear correlation. Now these tests are a little bit easier because we don't have to do very much work to come up with our null and alternative hypotheses. For linear correlation tests, the hypotheses are always like this. The null hypothesis is that capital R equals 0, saying there's no linear correlation. The alternative hypothesis is that R is not equal to 0, and that implies that there is a linear correlation. Our test statistic formula for this hypothesis test is T sub 0, and notice that the T here means that we're using the T distribution. The R in here is the correlation coefficient. So we have R over the square root of 1 minus R squared over n minus 2. N is the number of data points that we have. So it's our sample size. Then to find the p-value, remember we're using the T distribution since the test statistic has a T, and we use n minus 2 degrees of freedom. And because our alternative hypothesis is always going to be not equal to, that means this is always going to be a two-tailed test. Let's do an example. If we go back to our study on colas and bone mineral density, we found that the correlation coefficient R for the sample data was negative 0.806. We're going to use that to conduct a hypothesis test of the claim that there's a linear relationship between the number of colas drunk per week and the bone mineral density in women. So step 1 is to write our claim. This would be that there is a linear relationship between the number of colas drunk per week and bone mineral density in women. We're going to translate this into our alternative hypothesis. This part's easy because it's always going to be the same. So our alternative hypothesis is that R is not equal to 0, or if we want to put it in words, it would be there is a linear correlation. Our null hypothesis is that R is equal to 0 and there is not a linear correlation. For step 2, a type 1 error here would be supporting the claim of a linear correlation when there actually is not one. If we say the consequences in this case are somewhat serious, we could set our significance level at 0.05. All right, for step 3, we're finding our test statistic. So we're using this formula to calculate it. The R from our sample was negative 0.806. Our sample size was 15. So here's our calculation by hand of our test statistic. We get negative 4.91. The next step is to find our p-value. We have to remember that we had a not equal to in our alternative hypothesis. That makes this a two-tailed test. And in step 3, we found our test statistic to be negative 4.91. So because this is a two-tailed test and our test statistic is negative, that means that we're looking at the left tail of our t-distribution in order to find our p-value. So here's our t-distribution. Here's our test statistic of negative 4.91. We're shading to the left of that, and we're trying to find the area under this curve. Once we find that, we'll multiply by 2 because it's a two-tailed test. In order to find this area first, we would use TCDF on your calculator. And again, since we're doing the left tail, we're going to start at a big negative value, so negative 10,000, go up to our test statistic of negative 4.91, and we have 13 degrees of freedom. So that gives us 0.00014. So that's the area under this tail of the curve. Since we had a two-tailed test, we're going to multiply this by 2 to get our p-value. So our p-value turns out to be 0.00028. Now we can also get this value from StatCrunch in what we did to get our linear correlation coefficient. It also showed us this information. And what we're going to look at for this is where it says slope. So we want to look at the slope row of this table, and notice it gives us our t-statistic, which is very close to the one we came up with. We had negative 4.91, and this is negative 4.903. And this gives the p-value as being 0.0003, same as what we would get if we rounded this to 4 decimal places. Okay, so our next step is to compare our p-value to alpha and get our initial conclusion. Our p-value is 0.00028. Our alpha was 0.05. So our inequality looks like this. And this is a true statement since this value is less than or equal to 0.05. So we're going to have a positive conclusion, which is reject the null hypothesis. For step 5, we'll also have a positive conclusion, and we just write it out in a sentence. So we would say there is sufficient evidence to support the claim that there's a linear relationship between the number of colas drunk per week and bone mineral density in women. Now remember with all this that the methods we're learning in this section apply to a linear correlation. Even if we conclude that there doesn't seem to be a linear correlation, remember that it's possible there might be some other association that's not linear. Let's look at another example. A study was conducted at a hospital suspected of inflating charges for older patients. Data was collected for a sample of 30 patients with similar diagnoses with the following results. So we have our summary statistics for charges and patient age, and here are our simple linear regression results. So notice down here our correlation coefficient comes out to be 0.194. And now we're going to use that to conduct a hypothesis test of the claim that there's a linear correlation between patient age and hospital charges. When we do that linear regression on StatCrunch, it also gives us a scatter plot, and it goes ahead and draws a line in there. So here's what our scatter plot looks like. Now the test statistic for this test turns out to be 1.046. The p-value is going to be 2 times t-CDF of 1.046, 10,028, and that's going to be 0.3045. Since this is a large p-value, it will not be less than or equal to alpha. We'll have negative conclusions. So our final conclusion for this would be that there's not sufficient evidence to support the claim of a linear correlation between patient age and hospital charges. So now let's look at some common errors involving correlation. Number 1, even if we do find that there appears to be a linear correlation between 2 variables, that does not mean that one causes the other. So correlation and causality are 2 different things. Another common error is using averages. Averages tend to suppress individual variation, so they might inflate the correlation coefficient. And third, there might be some relationship between x and y, even if there's not a linear one. Okay, now let's go on to section 4.2. In this one, we're going to find the equation of the straight line that best fits our paired sample data. If there is a linear relationship between the 2 variables, this equation will algebraically describe that relationship. This best fitting straight line is called a regression line, and its equation is called the regression equation. So the regression equation expresses a relationship between x, which we call the explanatory variable or the predictor variable or the independent variable, and y, which we can call the response variable or the dependent variable. The typical equation of a straight line, y equals mx plus b, is expressed in the form y hat equals b sub 0 plus b sub 1 x, where b sub 0 is the y-intercept of the line and b sub 1 is the slope of the line. So our regression equation, given a collection of paired data, the regression equation y hat equals b sub 0 plus b sub 1 x, algebraically describes the relationship between the two variables. And the line that is the graph of this equation is called the regression line. It's also called the line of best fit or the least squares line. And what this line does is it minimizes the sum of the squared errors or residuals. The errors or the residuals are the differences between the observed values and the predicted values of y. The requirements for this, first of all, the sample of paired data has to be a random sample and it has to be quantitative data. Second, visual examination of the scatter plot has to show that the points approximate a straight line pattern. Third, any outliers must be removed if they're known to be errors. If they're not known to be errors, then at least consider the effects of any outliers. Here's an example. If we use technology to find the equation of the regression line in our situation with the colas drunk per week and the bone mineral density, this is that same procedure in StatCrunch that we use to find the correlation coefficient. It also gives us our regression line. So our regression line is right here. So we would write this out as y hat equals 0.8861 minus 0.0029x. Notice that in StatCrunch, it gives you the names of the variables instead of x and y. So the one that's on this side of the equation is the x, the one that's on this side is the y hat. This will also give you the scatter plot with the regression line drawn in. So the line in red is the regression line. Earlier we did a hypothesis test that showed that there is a linear correlation between the two variables. So that means that we can actually use the regression line to predict bone mineral density given the number of colas drunk per week. Example, for a woman who drinks 9 colas per week, we would predict that her bone mineral density is this. Notice all we're doing is taking our regression equation and putting in 9 in place of the x. That turns out to be 0.86 grams per centimeter squared. So that would be her bone mineral density. For a woman who drinks 2 colas per week, our predicted bone mineral density would be 0.8803. Notice in this one we're plugging in 2 in place of the x. And if we look at the scatter plot and the line up here, for the woman who drinks 9 per week, that value would actually be over here where x is equal to 9, and our y value would be wherever our y value is on that line. For the 2, we're looking at the point on the line where x is 2. So the value we came out with, 0.8803, is the y value for this point right here. Now when we're trying to use our regression equation for predictions, we can only do this if, number 1, the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. So in other words, we need to look at the scatter plot and the regression line. Also, if we conduct a hypothesis test for a linear correlation and it indicates that there is a linear correlation between the two variables, that's why we do the hypothesis test. And the third thing is that the data don't go too much beyond the scope of the available sample data. Predicting too far beyond the scope of the available sample data is called extrapolation, and it can result in bad predictions. Now, if we don't have these 3 conditions met, then that would mean that our regression equation is not a good model to predict our y values. So in that case, the best predicted value of y is just the mean of the y values. Okay, so here's a little flow chart for doing this. If we want to predict values of y, first we have to look at whether the regression equation is a good model. So here are the three questions that we have to answer. If the answer to all three of these is yes, then the regression equation is a good model, and all we do is substitute our value of x into our regression equation, and that gives us our value for y hat, our predicted value. If the answer to any of these is no, then our regression equation is not a good model, and in that case it doesn't matter what our x value is, because our best predicted value of y is just going to be the mean of the y values. So in this example of hospital charges and patient age, we determined that there was not a linear relationship between the two. In that case, if we wanted to predict hospital charges for an 80-year-old man, we would get the same answer as we would for a 20-year-old man, which would just be the average charge from our sample data. So the mean of our charges from our sample data was $7,647.36. So that would be our predicted charge for an 80-year-old patient or for any age patient. Well, that was the end of section 4.2. The rest of this video is going to talk about section 4.3, which is about residuals and residual analysis. Now, the next thing we need to talk about is residuals. So for a pair of sample x and y values, the residual is the difference between the observed sample value of y and the y value that's predicted by using their regression equation. In other words, the residual is the observed minus the predicted, or y minus y hat. Here's kind of what this looks like on the graph. So here would be our data points. So these values came from our sample data, the points in blue. The blue line is the regression line. So for example, if we're looking at this value of x, if our x is equal to 1, then the y value for this point would be our observed value. The y value on the line would be our predicted value. Our residual is the observed minus the predicted, just for the y values. So from here, this was at about 4, and this looks like it's at 9. 4 minus 9 is negative 5. So that would be the residual for x equal to 1. If we do x equal to 2, then we have our data point up here at 24. Our point on the line is down here at 13. So the residual, again, is observed minus predicted, so that would be a positive 11. So notice that if the point is above the line, then the residual is positive. If the point is below the line, then the residual is negative. Now, a straight line satisfied the least squares property if the sum of the squares of the residuals is the smallest sum possible. So that's what we're going for. A residual plot is a scatter plot of the xy values after each of their y coordinate values has been replaced by the residual value. In other words, we're plotting the x values with the residual values. And when we look at a residual plot, we're looking for a pattern in the way the points are configured. And we want to not find a pattern. So a residual plot should not have an obvious pattern in it. It also shouldn't become thicker or thinner when we go from left to right. Okay, so here's our original scatter plot and our regression line for the colas versus bone mineral density problem. So if we want to do a residual plot, that means we're going to take each x value. So for example, at x equals 0, x equals 1, and then for each of these data points, we're going to find the residual. Okay, so for x equals 0 here, we had two different data points. We had one below the line and one above the line. So notice in our residuals, here is 0, So our residual plot actually goes below 0 and above 0. And notice that for this point, since it was below the line, our residual is negative. For this point, which was above the line, our residual is positive. And notice for some of these other ones where the point is very close to the line, then our residual is very small. Okay, here's some examples of residual plots that either do or don't represent a good model. So in this one, again, we're looking for patterns in these. If we have a pattern in the residual plot, that's a bad thing. So this one really doesn't show any kind of pattern that suggests that the regression equation is a good model. In this one, we can see a pattern. So that would tell us that the regression equation is probably not a good model. Here's one where we start out over here with the points being very close, the residuals being very small, and then as we go out this way, they get much bigger. So the plot is becoming thicker. That says that the regression equation is not a good model. Okay, so for our complete regression analysis, first we want to construct a scatter plot and verify that the pattern of the points is approximately a straight line pattern without outliers. If there are outliers, we consider their effects by comparing results that include the outliers to results that exclude the outliers. Then we want to construct a residual plot and verify that there's no pattern. Also verify that the residual plot doesn't become thicker or thinner going from left to right. Okay, one more thing that we need to define. So assume that we have a collection of paired data containing the sample point xy, that y hat is the predicted value of y from the regression equation, and that the mean of the sample values is y bar. The total deviation of xy is the vertical distance from y to y bar. So the distance between the point xy and the horizontal line that represents our sample mean y bar. The explained deviation is the distance between y hat, which was our predicted value, and y bar, which is the mean of our y's. The unexplained deviation is the rest of it, so that's the vertical distance between y and y hat. This is the same as our residual. Now finally, our coefficient of determination is the amount of variation in y that's explained by the regression line. And the coefficient of determination is r squared, and that is actually when we're talking about our r, which was our correlation coefficient, this is the same r. So if we took our correlation coefficient and squared it, we get our coefficient of determination. The value of r squared is the proportion of the variation in y that's explained by the linear relationship between x and y. Okay, so in our previous example, the coefficient of determination was 0.649. And notice StatCrunch gives it to you right here underneath the correlation coefficient. So there's r squared. And what this tells us is that approximately 65% of the variation in bone mineral density is explained by the linear relationship.